Welcome to the Crazy Hot Chemist. So here we go, starting a whole new series here on chemical kinetics. I can't wait for this one. We got two slides here showing the outline of the entire unit here. So there's the first slide. Here's the second slide. So let's get moving. Bam! So here we go. Chemical kinetics and factors affecting reaction rates. So thermodynamics determines whether or not a reaction is reactant or product favored. However, this provides no information on how fast a reaction will actually transition from the reactants to the products. That's what chemical kinetics is all about. So chemical kinetics is the study of the speed, i.e. the rate of a reaction, as well as the mechanism, the stepwise process of how a reaction proceeds from the reactants to the products. So here are some things that affect the reaction rate. Number one is an increase in concentration. An increase in concentration typically increases the rate. So here's an example here. I have two test tubes, and inside each test tube is the same amount of magnesium ribbon. And what we're going to do is we're going to add hydrochloric acid to both of those test tubes, the same volume but different concentrations. So on the left-hand test tube is going to be a 0.1 molar hydrochloric acid, and on the right-hand test tube is going to be a 6 molar hydrochloric acid. So in a little bit of time there, immediately upon adding the two different hydrochloric acid concentrations, you should see the test tube on the left is now reacting, but slowly. There are some bubbles there, and the test tube on the right is reacting vigorously. In fact, it's so vigorous that after a couple of seconds, there's no more magnesium ribbon left over on the right-hand test tube, whereas the left-hand test tube is going to be reacting there for, at least 30 minutes or so. So an increase in concentration increases the rate of the reaction. Number two, the physical state. The physical state of both the reactants and the products, i.e. whether or not they're a solid, liquid, or a gas, greatly will affect the rate. Okay? So, Lycopodium powder is this really cool thing. It's that's otherwise known as dragon's breath. So, check this out. And Lycopodium powder is actually the spores to a club moss fern. And on the underside of the fern, you have these spores. And if you were to light on fire these spores, they would take a long time to light on fire with a match. However, if you grind up those spores into a very fine powder, very similar to flour, okay, then you get this powder. It's this yellowy powder, and you should see this beaker that I have here is filled with water, and then I've taken this Lycopodium powder and sprinkled it on top of the water, and it's very hydrophobic. The Lycopodium powder is hydrophobic, and it floats on top of the water because it's very light. So it doesn't like to interact with water. That's the hydrophobic. Now what I'm going to do is I'm going to take my fingers and I'm going to stick my fingers inside there, and you should see my fingers are inside, pushing down into the Lycopodium powder, and my fingers are like right inside the water. But yet, if I pull my fingers out of that beaker there, they'll be completely dry because they're covered in Lycopodium powder. Now what I want you to do is take a look at that little slide there with the periodic table partially on there, and this is in my lab. And now we're going to spray some Lycopodium powder right over the flame of a Bunsen burner. And this is what will happen. Check this out. Whoa, that's why it's called dragon's breath, because it's super cool. Okay, so here we go. Physical state. So you should see that Lycopodium powder before it's a powder will not burn, but yet as a powder it is very flammable. This is why metal shops that are grinding metal, sawing metal, polishing metal, sanding metal, drilling metal, you want to make sure that there's no flame nearby, because they will go up in flames. Same with corn silos. There's a vent on the top of a corn silo to make sure that those corn silos won't just explode, because a little tiny bit of a spark will set that whole thing up in flames. Number 3, an increase in the temperature generally increases the kinetic energy, of course, and then therefore the rate will increase as well. So an example of that is blue food coloring. So I have right here this reaction between blue food coloring and bleach. Okay, the beaker on the left-hand side is 2 drops of blue food coloring, and it's at 24 degrees Celsius. That's room temperature. The beaker on the right is 2 drops of blue food coloring and the same amount of water, and that's at 60 degrees Celsius. Okay, now I'm going to place in each of these the same amount of bleach, which is sodium hypochlorite. And over time, you should see what happens here. I have the thermometers in here, and you should see that the beaker on the right, which is at the higher temperature, which has more kinetic energy. So the molecules in the water are moving faster, so therefore this reaction will happen faster. Okay, so that's why that this beaker on the right is lighter in color, because there's the reaction is happening faster, and the rate is happening faster. There's a faster reaction between the blue dye and the bleach itself. Okay? All right, and then the next thing here, number 4, is a catalyst. A catalyst lowers the activation energy barrier, and that allows the reactants to proceed to products much faster. Okay? And here's an example of this. This is a reaction between hydrogen peroxide, and the catalyst here is manganese dioxide. Okay, and you get water and oxygen gas, and then of course manganese dioxide back again, because a catalyst actually doesn't react with it, okay, because you get it back, whatever you put into it as far as the amount of a catalyst, you get it right back out on the product side. Okay, and you should see with this graph that I have here, okay, the high graph is without a catalyst. So you should see that that barrier, that red graph, is a very high barrier, and the lower blue graph, the lower blue line, is much lower. So the activation energy barrier has been dropped. So it's kind of like if you want to scale a wall, then without a catalyst, there's a really high wall, you want to climb over that. Okay, now if you add a catalyst to it, then what you have effectively done is like tear down much of the wall, and now you can just step over the wall and get to the other side. The reactants are on one side, the products are on the other side. Notice that on this graph here, the reactants are at the same level, whether there's a catalyst or not, and the products are at the same level, whether there's a catalyst or not. Okay, so that gives you some ideas about how different things affect reaction rates. You got 4 things. You got concentration, state of matter, you got temperature, and a catalyst. And we're going to be taking advantage of all of these in this unit of chemical kinetics. Okay, I am the Crazy Hat Chemist, and of course we can't do this without a crazy hat. You want to subscribe to my video and subscribe to my YouTube channel. Give me a thumbs up on this video, please, and I will see you next time for more chemical kinetics problems. Bye now.